So let's say you need 100 electrons to neutralize the holes. Okay, let's say 100 electrons are pulled from this region, they move from this region and neutralize holes. So it would form a wider depletion layer. In case of a heavily doped diode, what happens? The electrons are so dense that 100 electrons would be somewhere near about the junction, right? बहुत पास में ही होंगे. Okay, you know, far away electrons need not move in this case. Only the nearby electrons can move and form a layer of 100 negatively charged ions, right? So the formation of same number of ions this time requires only a narrow depletion layer. So this time the depletion layer would be narrow but dense, it would be more dense as compared to the upper case, because same number of ions are packed in narrow region. Okay, you need same number of ions because you need same electric field to stop further movement. Right? कुछ आया क्या? Okay, I guess volume का issue. Okay. So I guess you are getting the point. In case of heavily doped diode, what happens? The width is narrower. So this time the electrons would not be able to get that much distance for acceleration, for accelerating, right? इसमें width ज़्यादा थी, they got ample amount of time to gain energy. This time the width is less, they are not getting that much amount of distance to accelerate to high energies, right? So now what happens then? In this case, when P and N are heavily doped, okay, when they are heavily doped, there would be hardly any minority charge carrier, hardly any minority charge carrier. So, and that too, even if there is a minority charge carrier, it won't be able to gather enough energy to break the bonds, right? It won't be able to gather enough energy to break the bonds, because width kam hai na, less width, it would get less distance to accelerate. Okay, so now this, so there would not be a indirect bond breakage. Okay, indirect bond breakage. This time it would be direct bond breakage. You call it field emission. Remember, electric field apply करके electron को pull out करते हैं. The electric field would be high, obviously. Okay, because even in this scenario, the number of ions in the depletion layer is same as in the previous case. So the electric field would obviously be of same order, but it's like the width is less. Also the external electric field would also be there. Okay, so what happens actually? The silicon bonds would all of them would be stronger relatively, or identical strength के होंगे, right? While the bonds of silicon with the dopant would not be that strong. So they start releasing electrons because of very high electric field. They start releasing electrons. So an electron is released in this direction, while a hole is released in this direction. So electron hole pair are produced in the depletion layer itself, and because of the barrier field, they are separated. As soon as they are formed, they are separated in opposite direction. So there is some current, okay, large amount of current, but still there is no permanent damage because the lattice structure has not been broken as in this case. यहाँ पे क्या हुआ था? The electrons, high energy electrons were coming and they were breaking all the bonds, any possible bond, silicon का किसी का भी हो, they were not differentiating. Here it's like particularly differentiated thing. Okay, the dopants are releasing the electrons, right? So this is called Zener breakdown. Okay, and it is only for heavily doped diodes. Okay, Zener breakdown is used in a special purpose diode called Zener diode. Okay, we would be using that, studying that. Shall we start? आगे बढ़े. You know, the questions on diodes are really simple. I'll explain. I'll give you one question. These are 4 arrangements, okay, in which case the diode would conduct. In which case the diode conducts. Okay, थोड़ा छोटा लिखा है, but it's this. Tell me which one? D. सबको समझ आ गया होगा तो नहीं. The P side should be at higher potential as compared to the N side. This is in this case. इस case में it's not connected to any battery, so no conduction. Here P side is on the lower, is at the lower potential. Here also it's at the lower potential. So it's D. And for your kind information, it was asked in 2016 JEE mains. है ना? Ultra easy, right? But not all of them would be that easy. But questions from diode are generally easy. From transistor they are little complicated, very little, not much. Okay, still easy. As compared to what all you have seen, this is like the easiest of all. The topic is theoretical, that's why people generally tend to ignore it, leave it. But please hear this. These 2 chapters, this one semiconductor as well as communication, they both contribute 1 question each into the paper, and the questions are generally really easy. Okay, so please don't actually leave them. Okay, please go through them. 1 question is always asked from EM waves, 1 is from the experiments generally, है ना, Hertz experiment, what happened in that experiment, and something match type का question or something, that this discovery was made in what experiment. Okay, so 4 questions are like really piece of cake kind of questions. Okay, and you can actually solve them in less than a minute, all 4 of them, right? Acha, slightly better. This is a 10-volt battery. Okay. 1 kilo ohm. Okay. Now this is not an ideal diode. This is a real diode. Okay, for which knee voltage is 0.7 volt, which means it needs 0.7 volts at least for current to flow, right? Okay, and the resistance, forward resistance of diode is 100 ohms. So the question asks, tell me the current through the diode, ID. Tell me the current through the diode. करें? Now in this question you need to replace the diode. You can understand that it would conduct, है ना? समझ आ रहा है? Let us assume कि अच्छा it's not conducting, then the voltage, the current flows through this path. So the voltage across this would be 5 volt. 5 volt here as well. So it is more than the knee voltage, so obviously it would conduct. So in this case you need to think about it like this, that this is a battery of 0.7 volt when it is conducting. Okay, when it is not conducting you need to consider it as a open circuit. So when it is conducting it's like a battery of 0.7 volt and a resistance of 100 ohms, and this is the current. So can you find it? It's Kirchhoff's law, right? It's Kirchhoff's law. So I guess you remember the nodal method. We used to do this V, we used to take this as 0, right? है ना? And all three would be 0. So the nodal method used to say that from this branch the current coming down, the current going into this branch is V, actually here it is 10, we are taking this as 0, and instead of this I would prefer if we draw this battery on the lower side, makes things easier. So V minus 10 by 1000, here it is 0.7 volt, right? 0.7 volt. So the potential difference between these 2 points is V minus 0.7 upon 100. In this branch here it is 0. The potential difference is V minus 0 upon 1000 is V. Let's study application of the diodes, then we would study special purpose diodes. Application of diodes, and then we would be studying special purpose diodes. First application is like a switching device, as a switching device, okay, which you already know, so I won't be discussing. Second application is half wave rectifier. Many of you would be having this as your school project, right? कितने लोग हैं? 2 from here, and if I count the online people, I can admit that okay, 100 लोगों का तो कम से कम होगा. Out of all the students of Udaan, at least 100 would be having half wave rectifier as their school project. Another 100 would be having full wave rectifier as their school project, and rest 100 for and, or, and, not gate, right? That's it. So my school project was full wave rectifier for that matter. Transformer भी बनाया है. अच्छा, you have transformer as your project. Nice. So now here we use transformer. Achha, tell me this thing, what are these two parallel lines? What do these two parallel lines represent? These two parallel lines. They represent core. Please note, ये याद रखना हमेशा. Okay, they represent core. Okay, at times it's asked in your viva, so it's a viva question. ये क्या होता है? Soft iron core. Obviously, you cannot have hard iron core. It would be permanently magnetized in one cycle only. Okay, so now this is your diode. This is the load resistance, and the output is taken across the load resistance. Okay, let's discuss what happens. Let's say a sine wave comes. Okay, so when a positive cycle comes, this becomes positive, this becomes negative. Obviously, this would conduct, right? Okay, and the whole of input appears as output, so the output would be same. Slight drop in output is observed because the diode is not real. It would take out 0.7 volt for its own use, है ना? Okay, slight drop. Okay. Now, in case of negative cycle, this becomes positive, this becomes negative, no current, so the output is 0. Okay. So the output would be something like this. The output would be something like this, only positive cycles, positive portions. The negative portions are clipped, right? Now, important thing worth noting, when we were doing AC, we studied that for half cycle, the average current is 2 I naught by pi. Here, one half produces this average, other half produces 0 average. So the average for complete cycle is आधा, हाफ नहीं होगी, हाँ. So for complete cycle, it is I average is I naught by pi. Obviously, you can integrate. This portion would not contribute anything, and this portion would contribute, but the time would be 0 to t. If you remember, there we were doing this thing. I naught sine omega t dt, and the time with which we were dividing was 0 to t by 2 for half cycle, and the integration was 0 to t by 2. Here the integration would be 0 to t, but this second half portion contributes nothing. So actually it has to be integrated till 0 to t by 2 only. Okay, but the time here would be full time period. So a factor of 2 is removed from numerator, right? That's why. So the average current is this. Another important factor, in the negative half cycle, whole of the secondary voltage appears across this, right? Because it is like an open circuit. When no current is flowing, resistor causes no drop in voltage, so whole of the voltage appears across Vs. So actually the breakdown voltage of diode should be higher than the secondary voltage of the transformer. Otherwise what happens? It would break down. So एक बार breakdown हुआ. So if it's a normal diode, then it would behave like a resistance. फिर क्या आपको AC मिलेगा ऐसा, right? Okay. So V breakdown should be more than Vs for normal operation. Another thing, these peaks we get, these are called ripples. C में होता है ना ripples. The waves we see in water are called ripples. So they are like sea waves coming and hitting y-axis. They are like sea waves coming and hitting y-axis, right? These are called ripples. Okay. Okay. For AC, the frequency is 50 hertz. In one cycle of AC, one ripple is produced. So basically 50 hertz is the frequency of AC and 50 hertz would be the frequency of ripples. Why? Because एक cycle में एक ripple produce होता है. So in 50 cycles it would be 50 ripples. So ripple frequency is 50 hertz. Okay. There are some more aspects, but we would discuss them a little later when we finish full wave as well. Okay, aspects of filtering actually. Shall I raise this? Second part is full wave rectifier. Okay, full wave rectifier. it's quite similar to the previous scenario, except that there is a center tap and two diodes. Why do we need a center tap? Let's first draw the diagram without center tap. Let's say I draw this. Now what happens if I connect this, if positive cycle comes, this would conduct, this would not conduct, right? And vice versa, this would conduct and this would not conduct. So we need some arrangement to send the current back, which is through center tap. Okay, there is a center tap. Its purpose is to divide the secondary voltage into two parts, Vs by 2 and this is Vs by 2. Right, when positive cycle comes. Okay, let's take the center tap as 0, reference level 0, right, for our ease. Is it okay? For our purpose, let's take it as 0. Okay, so what happens actually? Current flows like this. The upper diode conducts and the current flows through load resistance. Okay, the output in this case would be Vs by 2. You can see actually only Vs by 2 is appearing. The lower half of transformer is not contributing, right? So it's a positive. Look, this end is positive, this end is negative. So let's draw the output curve. The output curve is this peak value is Vs by 2, right? Now what happens? In the lower portion, in the second half cycle, this happens. This happens. So this conducts. This conducts. This is positive. This is negative. Right? This is positive. This is negative. What happens? The output is again of same polarity and of the same value. Right? So it is another lobe on the positive side. So only positive lobes would be there. So you can see we have converted the negative portion to positive, but we lost half of the secondary voltage for every cycle, right? Okay. Another thing worth noting is every cycle contributes 2 ripples here. Every cycle contributes 2 ripples. The ripple frequency would be 100, right, in 1 second. For 50 cycles, 100 ripples would be produced. The ripple frequency is 100 hertz. And what would be the average current? By pi, yes, obviously. For 1 half cycle, it is 2 I naught by pi. For 2 half cycles, it is again 2 I naught by pi, right? Okay. Now let's talk about breakdown voltage scenario. Let's say this is a positive half cycle scenario. Okay. Till this point, the voltage is plus Vs by 2. Here the voltage is minus Vs by 2. Okay. This I am writing considering 0 at the center tap. Okay. The potential difference between the diode terminals would be Vs. Okay. So here also the breakdown voltage should be more than Vs. Okay. Even though we are getting half output, but the diode is still equally likely to break down as in the previous case, right? Okay. For normal operation. Okay. Acha, tell me what would be the RMS in this case? Can you find the RMS? कितनी होगी? सब सॉल्व करने लगे. You don't need to find RMS. हाँ, same होगी, right? In this scenario, the RMS is I naught by root 2 for complete cycle, even for half cycle, because the two portions are symmetrical. So here the RMS would be same for half cycle, complete cycle as well, because RMS is like, you know, squaring हो रही होती है, that's why even negative values are added, right? So I RMS is same I naught by root 2. Shall I remove, shall I erase this? आप लोग लिख लो ये. करें? चलो, I'll erase this. And let's discuss what was the purpose of rectifier? Yeah, the purpose of rectifier was AC to DC conversion, right? But the problem, you understand the problem here? It's not pure DC you are getting, right? It's variable DC. It's, you know, changing the magnitude, not smooth, right? Right. So we need, we actually can say that the DC we receive, we get here, is not complete DC. It's not pure DC. It's actually a mixture of DC as well as AC signals, and we need to filter out the AC signals so that we get pure DC or at least nearly pure DC, है ना? So we need filter circuits for them. Filter circuits, the first one is capacitive filter. Let's say this is the load resistance RL. A capacitive filter is connected in parallel with RL. What is the purpose? Here this is unregulated, unfiltered supply. It may be half wave, it may be full wave, doesn't matter really. Okay, so what happens actually, you remember that the capacitive reactance was 1 by omega C, okay, that the capacitor had infinite reactance for frequency 0, which is DC, and capacitor had low reactance for high frequency AC, okay, which means if this has AC as well as DC components, what happens? AC would bypass through it, right? Okay, AC would bypass through it, AC would go through it because it provides a easy path for AC, right? While the DC is blocked, so DC reaches the output terminals. So the output in this case would be a lot smoother. Unlike that, it would be a lot smoother. नहीं समझ आया? It has AC. Here you feed AC plus DC, right? For AC, capacitor is a low reactance path, so AC can go via this while DC is blocked. So DC would appear on the terminals, AC would not, right? Second one is inductive filter. You need, for this purpose, you need what? low frequency या high frequency capacitor, low value or high value capacitor? You need C high so that this reactance is very low for AC. Okay, it's totally free way for AC. So the capacitor needed here is high to make XC really low. Okay. Second one is inductive filter. In fact, it's like this. I hope everyone can see. An inductor is placed in series. The capacitor was in parallel, it's placed in series, right? Now, here the logic is that XL is omega L, okay? When frequency is high, XL is high. So it blocks AC, right? It blocks AC. So it would block AC while it would allow DC to go through. Okay, so only DC is received, again similar type of output. Shall I raise it? And you would need inductor high as well. L should be high as well, so that XL is very high. So that XL is very high. Shall I raise this now? अभी भी नहीं. करें अब तो करें थर्ड वाला. The third one and the best for our purpose okay, the third one is LC filter. It's a combination of both. So what happens, you place an inductor in series and a capacitor in parallel like this. Now you can understand, if you supply AC plus DC, okay, or impure DC basically, variable DC, what happens? The capacitor blocks AC signals while inductor blocks the AC signals while the capacitor allows AC signals to bypass. So basically in first stage most of the AC signals are blocked, while if some of them pass through, they are bypassed through the capacitor. So it gives almost pure DC, right? Here, but what we try that the frequency of AC should be more or less near to the frequency of resonance, which is 1 by 2 pi root LC. In that case, what happens? Minimum impedance is offered to flow of AC portion. Okay, so the AC portion, it gets minimum impedance, so it bypasses. Okay. Correct? Shall we do? Chalo. Our question was asked on this LC filter, okay, and I don't remember the year. Actually, I think it was 13 or 14, in which the value of capacitor was asked, the range of values. So as I said, the capacitor should be selected or the inductor should be selected so that the frequency, the resonant frequency, is almost equal to the frequency of AC source, right? So only that was needed to be calculated, but it's like very difficult. It appears very difficult. So most of the students, they left the question that year. So let's discuss some special diodes, special purpose diodes. The first one is Zener. Okay, first one is Zener diode. A Zener diode is a heavily doped PN junction. It's a heavily doped PN junction. Okay. Very nice. It's a heavily doped PN junction diode. Okay. And it undergoes Zener breakdown in reverse mode. So it undergoes Zener breakdown. Okay. In forward mode, it behaves like a normal diode. Okay. Normal diode behavior in forward mode. Right? Now, why is it used? Why was it made? It was made to form voltage regulators, to manufacture voltage regulators. So the use is voltage regulator, and many questions had been asked in Cbse as well as once or twice in JEE as well on voltage regulator. Let's discuss a voltage regulator. Let's say this is Vi, this is unregulated supply. Okay. What does unregulated supply means? It means it is not constant. At times, spikes of high voltage, they come. Okay. So it's a DC supply, but with some spikes of high voltage. Okay. And this is a not here. Let's write it here. This is a series resistance. This is the diode. The symbol of this diode is this. Okay. the corners are bent, and this is the load. This is Zener diode. The output is taken here, or shall I say here. Okay, this is the output. So let's discuss how it works. For our purpose, I hope you have written all this, है ना? If anybody hasn't, please do it. I would be needing some space. Shall we start? Now, how it operates, let's discuss. Let's say the input voltage is like this. It's increasing linearly. And let's discuss the output. So, till the time the input voltage is increasing, let's say its breakdown voltage is Vz. It's called Zener voltage, right? The breakdown voltage is Zener voltage. Okay. So, till the time the voltage across this branch is lesser than Vz, the diode is reverse biased. It's always used in reverse mode, because in forward mode it's a normal diode. You don't need heavily doped diodes for normal operation. They are costly, right? So, if the voltage of this branch or output, you can say, is lesser than the Zener voltage, what happens? The diode is off. So, only whatever is the input, some part of it appears in the output. Some part, not all of it can appear, because some drop would be there in this branch, right? Right? Okay. So, output is also increasing. A time comes when the voltage across this branch or the output is, it reaches Vz. When this comes, this diode goes into breakdown mode, okay, which means it allows large amount of current to flow through this branch, and in return the current through the resistance remains constant. The extra current is absorbed by this Zener diode. So, I can actually draw this as a reverse battery with voltage Vz. Getting my point? It's like a reverse battery with voltage Vz. As long as the voltage across this branch is more than Vz, this would behave like a reverse battery. So, what happens? Because of this reverse battery Vz, the potential difference, these two branches are in parallel, the potential difference in output would be Vz itself. So, the output would be Vz. Getting my point? So, let's take few numbers. Let's say the Vz for this diode is 50. Okay. So, let's say you increase the voltage, and at 60 volt, when the input is 60, the voltage here is 50. Let's assume this. So, what happens when voltage here is 50? This goes into breakdown mode and behaves like a reverse battery. So, the output is 50 here. If the input increases to 61, still the output here is 50. Okay. If the input increases to 100, still the output is 50. So what happens to rest of the voltage? The rest of the voltage is handled by this resistor. Okay, you can see this is series to both the branches, right? So what happens? If the voltage is 100, in this portion the voltage is 50. If the input voltage is 100, in this portion the voltage is 50, rest 50 is handled by this. So it handles a lot of voltage, and so a lot of current is also, it also flows. Lot of current also flows. So this handles large current, large voltage. This blows off if the voltage is really high. Okay, so your appliances are safe. Okay, you can understand, since the input is since the output is constant, the current through load resistance I load would be Vz by RL. Can you understand this? So the current through the appliances would remain constant, right? Because the output remains constant. Is it okay? So if the input continues increasing, this handles the extra voltage, while the extra current goes through the Zener diode. इस branch में the current fixed है ना? The current here is fixed. This is load current. This is fixed. So what happens? The extra current is absorbed by the Zener diode. It goes through the Zener diode. Is it okay? So you understand, the output is regulated while the input is increasing. This may happen that this blows off and the output is 0 then, but your appliances are safe, right? Okay. This is for small electronic devices. For AC and all, please try to understand, we cannot use a Zener diode. It's a very small device, right? So we use heavier devices, power electronic devices. Okay, power electronics devices, not these small semiconductor electronics devices. Is it okay? So let's go for a question. Shall I raise this? A previous year question, I don't remember which year, but those who didn't draw, please draw two separate diagrams. One is the diode connected here, the other is diode behaving like a reverse battery. Okay, please draw two separate diagrams, don't cram it into one thing. ठीक है? In this case, you need to find the total current I and the load current IL. In fact, find all three currents. Total current I, the load current IL, the Zener current IZ. IL and IZ. Now this is a very easy question, you know it. हो गया होगा अभी तक तो. Anyone online? Online people, please solve this. This is a very easy question. This is like current electricity of class 10th. अरे हुआ नहीं. First of all, let's check whether the diode goes into breakdown or not. 30 volt. Let's imagine the diode is in cutoff mode. Is it okay? The diode is in cutoff mode or reverse mode. So it is open circuited, right? So only two resistances are there, 1 kilo ohm and 1 kilo ohm. So the voltage distributed would be 15 volt here and 15 volt here. Is it okay? And because the voltage here is 15 volt, the diode also has 15 volt across it. It goes into breakdown. So what happens? The voltage here is 12 now, and in this branch also it is 12. So you can find the current in this branch. IL would be how much? 12 upon 1000. Can I call it 12 milliampere? Right? Rest 18 is handled by this voltage. So the total current through this I would be 18 volt upon 1000 or 18 milliampere. Right? Total current is 18 milliampere. Load current is 12 milliampere. So the Zener current, which is the remaining amount, 6 milliampere, right? The Zener current is 6 milliampere. Okay, the question is as simple as that. The questions in this topic, as I said, are easy. Shall I erase this? Huh? The second special purpose diode is, the first one was Zener, the second one is photodiode. Okay. A photodiode is a normal diode. Okay, it's a normal diode with let's say this is a photodiode, this is the depletion layer, and P side, N side. So P is made negative while N is made positive. Is a normal diode in reverse mode with a window. Here on the depletion layer there is a transparent window. Okay, while rest of it is covered in box. It is reverse. Oh, ulta ho gaya, sorry. Now it's okay. So it's reverse biased with a window on the depletion layer. So what happens? Since it is in reverse mode, there would be no majority charge carriers. Okay. For depletion layer, what happens? There are no charge carriers, but if I draw the band diagram, this is conduction band, this is valence band, it is filled with electrons. The electrons are still there, they are bonded, right? They are bonded. And the band gap is as per the need, let us assume it is 1.1 electron volt. Okay. So what happens when a photon is incident on a bond? What happens? The electrons from valence band, they jump to conduction band, okay, and start conducting. So what happens? An electron becomes free here. So a hole would also be formed here. So an electron hole pair is released, and because of the barrier field, they move in separate directions, right? This is negative. Electron moves in this direction and hole moves in this direction. They are instantly separated. So because of light, what happens? The charge carriers increase and there is increase in current. Okay. Obviously, it would be conducting in in dark mode as well, right? There would be, whenever there is no light, okay, there would be some reverse current, because even in reverse mode, a diode has some reverse current. Is it okay? So in the dark mode, there is some reverse current, while whenever light is incident whenever light is incident on the window, okay, what happens? Because of extra charge carriers, the current increases. Okay, this would happen even in case of forward biased mode as well, but we particularly use it in reverse mode. The reason is, in case of reverse mode, the current is very low. It is reverse saturation current, which is very low, microamperes. So even if there is very small increase in current, it is easily noticeable. Just imagine, in reverse mode, the current, the dark current was ID was 1 microampere. Okay, but what happens? Because of light, the current suddenly increases to 2 microampere. You can see the change is hardly 1 microampere. 1 microampere is nothing, but compared to the original value, this change appears huge, 100% change. In forward mode, the current is 1 milliampere normally. Now, in this case, if we we allow some light to fall on the junction, what happens? 1 microampere current increase is registered. So the total current now becomes, you can figure out, it's hardly 0.1% change. समझ आ रहा है? In forward mode, the current is high, so the change because of light is not noticeable, okay, compared to the original value. Percentage change is very less, while in reverse mode, the current is really low, so any change would be really noticeable. So that's why we use it in reverse mode. It is used in security systems. Okay, 1.1 electron volt is the energy of a photon in infrared region. Okay, so what happens in these security regions, and in these security devices, what happens? Infrared light source, we would just see that is LED, light emitting diode. It can produce light in infrared region as well. Okay, so an LED, infrared LED is kept here, while a photodiode is kept here. It produces infrared, which is incident through a lens. It is concentrated, focused, made a parallel beam basically. So this parallel beam falls on the photodiode. Whenever somebody crosses it, the beam is absorbed, disturbed, and the photodiode registers a drop in current, because till the time infrared beam is incident, high current would be there in reverse mode, and suddenly the current drops. That change is noticed, right? That change is noticed and alarm goes on, right? You have seen in movies, in all these thief based movies, in which they have some devices, some goggles and all, in which you can see infrared light ka pura jal, right? Pura mesh, a mesh of infrared light is there. They can see through goggles, aisa teda tel light hota hai, right? And they somehow do some arrangement, है ना? धुएं से भी होता है, कुछ तो ऐसा होता है, मतलब it's like, हाँ, Dhoom 2, 3, whatever. But this is the device actually. It's not that easy. वो तो movie होती है. not easy to crack these devices, right? Uh, so, kaise? Somebody is suggesting a solution. The third one is a LED, light emitting diode. Okay, a light emitting diode is exactly reverse of this device. Okay, here light is incident and conduction happens, there conduction happens and light is emitted. How? See, these are the device, these are made from special semiconductors. An example of this is gallium arsenide. Okay, this is used as a base semiconductor. Instead of silicon, we use gallium arsenide, okay, as the base, and we do some doping and all. The reason for using this is, for gallium arsenide the band gap is high. It's in the range of visible light. Okay, visible light का होता है 1.8 electron volt to शायद 2.5 ऐसा कुछ होता है. I don't remember the exact value. Please calculate it. Okay, you can calculate it. I would rather write it as E visible. Okay, the band gap is the band gap lies in visible range. Okay, so whenever this is the LED and this is P region, this is N, this is forward biased. So what happens in case of forward biased, the majority charge carriers are traveling like this, okay, holes, while the electrons are traveling like this. One thing may happen, that some of them get neutralized at the junction. There electron hole pair formation was happening, here electron hole pair neutralization is happening. So whenever they neutralize, okay, a photon is released and that photon lies in visible range. Let's check how. Whenever electron hole pair neutralize, it happens because the electron in conduction band falls into a valence band hole. Okay, this neutralization happens when conduction band electron falls into valence band hole. So a photon of this energy gap is released, okay, and depending on the energy gap, that is the color of light is visible. Okay, so let's draw the diagram for this. The IV curve for this would be, the infrared diodes are most easy to manufacture. You get it? The band gap is least. Normal diodes would be infrared diodes, okay, infrared LEDs. So they kick start early. This is IR. Okay, since the band gap is less voltage is needed to conduct, right? For red, this is the graph. For the rest, here it is for green, and here it is for white. Okay, in case of white, there are others as well. आप समझ गए ना? It would be green से आगे actually violet, indigo and blue are not emitted. You would hardly see a blue colored LED. कभी देखा है क्या? देखा है? You would hardly see. It's difficult to manufacture actually, but if it is there, it would find a place here as well. Diwali lights. Okay. Okay. So it would find a place here. For white, the band gap is maximum. Okay, the band gap is maximum. So what happens actually? All the photons of all possible colors are emitted. In that case, the violet photon is emitted. Rest all can also be emitted because collisions, absorption, and then radiation. This happens. It may happen ना, एक photon absorb हुआ and re-emit हो गया. That time it would be a less energy photon, so it would fall in some other color region. Okay, so white colored have the highest knee voltage right? Correct. Next device. Okay, the fourth one, solar cell. Okay, solar cell is a similar optical device. You know, we studied 3 optical devices, photodiode and LED, and this would be the third. Okay, Zener is not an optical device. These are the optical devices. Okay, let's say this is the junction. What is done generally? Either of the layer is cut in such a manner that, getting my point? It is cut in such a manner that you reach till junction layer. Okay, now sunlight is incident on this. Okay, the circuit is open. What happens? Because of sunlight, electron hole pair are formed. Okay, this is, let's say, P region, this is N. So the barrier field would be something like this. Electron hole pair are formed. They are instantly separated. The hole goes like this, right? They are instantly separated. And these electrons, they gather here, the holes gather here. Okay? So this continues, this separation procedure continues till the time the voltage here is equal to barrier voltage. So you know, for solar cell, special purpose materials are again used so that the barrier voltage is high, because more the barrier voltage, more would be the output of solar cell. Okay, okay, more would be the output of solar cell. So we you know, arrange them in series as well as in parallel. Okay, arrays of series and parallel cells are made. You have seen it, right? Is it okay? In fact, it has negligible thickness but great width. Why? Why? You want big depletion layer so that more and more light can fall on it, and in that case what happens? Not more electrons, but you know, if the width is large, obviously the voltage would be equal to the barrier voltage. But if width is large, more number of charge carriers can be produced when it is connected. Let's say I connect a resistance, the output power would be more. More area, more energy absorbed, so more power production, right? Okay, and you know, the beauty of solar cells is that these devices can work for 20 years without any issue. The only maintenance they want is washing their surface, because when dust settles, the intensity of light falls. So basically you need to wash their surface, that's it. Disconnect and wash, and then it's good to go, as good as new, right? That's the best thing about them. For all generators and other power plants and other sources, they involve moving parts. So lot of wear and tear, no moving parts, no wear and tear, right? So can I erase them? Can I erase the diagram? Now it's time for 3-layer device called transistor. We call it a junction transistor or simply transistor. Okay, it is a 3-layer device in which middle layer is made thin while the 2 layers are thicker but not of equal size. Obviously, the middle layer has to be different, otherwise what's the point? If you do like this PN, what's the use of it? It's PN junction, right? So the middle layer has to be different, PNP. Okay, this middle layer is called base. The bigger one is called collector, while the moderate sized is called emitter. It comes in 2 flavors, PNP and NPN, right? So let's discuss why base is made thin, why emitter, why collector are made in this manner. The base is lightly doped and thin. Okay? Why? Why? Because the purpose of base is to control the flow of charge carriers from emitter to collector. Okay? Its purpose is to control the flow. If you make the base thick, many of the charge carriers would be neutralized in the base itself. You don't need that. Okay? Thick hoga to more probability of settling here. Okay? Here with any of the electron, these holes would have more probability of settling here with any of the electrons, making the base positive. Okay? Depleting it with charge carriers, depleting it of charge carriers, right? So base is made lightly doped and thin, okay, and lightly doped because you don't want many charge carriers here, because if there are many charge carriers, these holes would settle here, combine with anyone and settle. Okay, emitter is the source of charges, so you need it to be heavily doped. More the doping, more is the amount of charge it can supply. It is moderate sized. Okay, while the collector is moderately doped and large sized. The reason for large size and moderate doping is, emitter is the source. You want large amount of charge carriers from there, so you need it to be heavily doped. But it has to collect those moving charge carriers. You don't need it to be heavily doped. You don't need it. Okay, so it would be meaningless to dope it, becomes costly, right? So you dope it moderately. The reason for large size is because these charge carriers which come from 2 layer back, they are coming with high energy, right? When they are collected here, they release their energy as heat. So it handles the maximum amount of heat of all 3 regions, right? And because of that, it needs larger surface area. So you make it large, so that more surface area is there, more heat is radiated. Okay? Okay. In the other one, I'll draw it. In the other one, the electrons are the majority charge carriers. Hole is of p type. The collector has electrons but less in number. Okay, this is the other type, and actually this is more used. The reason for that is since holes are less mobile. Okay, so PNP device, it involves major movement of holes, so it would produce lesser current for same voltage because the holes move slowly, right? So their drift velocity would be less, and I is NAEVD, right? I is NAEVD. If this is low, current would be low. So because of holes, the current would be low. For same voltage we want high current for less voltage, right? Okay, which means lesser resistance. Okay, so we would prefer NPN. So I'll erase PNP. Okay, we started with PNP, but we would not touch PNP any time now. We won't touch PNP anywhere. Okay, so let's discuss the transistor action. Transistor action. What is transistor action? I would tell you. Okay, now PN junction. There are. I'll make it a little larger for our reference. Obviously there would be two junctions, right? Now for majority charge carrier flow, you need this to be negative and this to be positive. So the battery is connected like this, negative positive. Okay, battery or biasing you call it. Biasing hota na, you are favoring one side compared to the other, so you are biasing it. So this junction is narrow because of forward biasing. Okay, but these charge carriers, they cannot travel like this. These electrons, what happens? There are large number of electrons here everywhere. These electrons cannot travel like this because this is thin area. Okay, if this happens, they would crowd this place. They would crowd the P region. Okay, because only narrow portion is there to leave. So what we do, we make this even more positive so that they go to the longer journey. Okay, they go for the longer journey. We do this by connecting this. Okay, so emitter is the most negative while collector is the most positive. Okay, this is the biasing. So here N is positive and P is negative. Collector is positive and P is negative. The base is negative for the second battery, right? So now the width should be high. So the width of Cb junction is high while the width of Eb junction is low. Okay, now let's understand the transistor action. Let's say right now the base is not connected. Okay, right now the base is not connected. What happens because of the battery action, the biasing, the electrons travel from here to here. Okay, and this battery is pulling them, so they would prefer going here as well, right? Okay, the majority charge carrier try to move like this, but the P side has some holes as well. Some of these electrons would sit in these holes, making the base negatively charged, right? Some of these electrons, these majority electrons from emitter, would sit in the holes of P of base and make the base negative. When this happens, when this crowding of base happens, this is negatively charged, it restricts the further flow of electrons. Okay, this restricts the further flow of electrons. So the current of this bigger picture, E to C, C to E, basically charge carriers from E to C and current is from C to E, right? So the charge carriers from E to C, this flow stops, reduces by a huge number, right? Okay, so very less amount of flow would be there now. Now what do you need to do? You need to pull out the charge, the electrons which are occupying the holes. You connect it. You start pulling out the electrons, or you can say you start supplying some current. When you pull out the electrons, the base is slightly cleared, कुछ हिस्सा, only some portion is cleared, the majority movement starts. If you supply more current, means you pull out more electrons, the base is further cleared, more majority charge carriers, and so on. So a time would come when there is no electrons occupying the base, and large amount of current would be flowing. Okay, so here it's like the P type, the base region, the middle portion is like a check valve. You know check valve? ऐसा होता है ना, बड़ा सा वाटर सप्लाई होता है, उसके ऊपर ऐसे गोल गोल लगा रहता है, जिसको यू टर्न इट एंड द वाटर सप्लाई स्टॉप्स. So it's like a check valve. It's behaving like a check valve or a bridge. Okay, what happens when there is crowding on the bridge? The flow of electrons stops, and whenever the traffic is removed, okay, the crowding is removed, the flow resumes. So base current, which is generally very small in amount, because you are removing very few electrons. छोटा सा तो base है, very small base, so you need to remove only few electrons. Okay, so for removing few electrons you need very less current. So through very less current you are controlling this larger current. This is like around 100 times larger. Okay, this majority flow. So through this current you are controlling this 100 times larger current. Okay, this action of transistor is called transistor action. Is it okay? Understand this? Okay, so what happens? I'll write here, due to biasing, electrons occupy holes in base. This stops E to C flow of majority electrons. Okay, if we supply some IB, comma, some holes are cleared, flow of electrons from E to C resumes. ठीक है, this all is transistor action. I have written in short form. Okay, this all is transistor action. बस done. Okay, chalo. So we would continue this tomorrow. Okay, I have a class tomorrow as well, and I hope we would be able to finish this chapter itself. So after tomorrow you would be having only communication and one extra topic, that is X-ray. It's still pending. Right? Okay. Thank you for the class.